Robert, the floor is all yours.
All right. Thank you very much. All right. Hello, everyone. I think I never had such a beautiful dressed audience than here. You all synced up today. That's amazing. So, as already mentioned, I'm a developer advocate at Google, based out of the London office, and about all things cloud, basically. And I like walks on the beach. Wait, that was a different talk. Well, what do I do actually? What is a developer advocate actually doing? So what we do, we understand our job as like a bi-directional connection between you guys who build on top of our platform and the people within Google that built the platform. So I really want to know what you build, how you build it, what your experience are. Give us constructive feedback, things like that. That's why you always also find me on Twitter and on other channels to connect to us, basically the whole group of developer advocates. Now, this picture in here is a picture from a travel of mine. So if I don't travel for work, I also travel sometimes for fun. And this is a picture where I did a rally between my hometown and Gambia, Banjul in Gambia. Which went through the Mauritanian desert, and that is one of the pictures there. So why did I put that in here? I'm always trying to, like, if you have this perspective of, like, we always talk about like greenfield applications and things like that, building on a green field. Now, this is not always possible, right? Like, if you're a company that is around for a while, you have applications that are like very critical to you and you cannot rewrite all the time everything new. So you have to find a balance between keeping running what you have already running and building new and innovate. So I want to try to bridge these two worlds today and what you can do basically on Google Cloud Platform to accommodate that. I hope, and I guess, that everyone knows this screen. And if you type in Utrecht or Amsterdam, you get about 500 million, so 500 million results within a second. And I think this is pretty impressive. But if I look at the screen, I'm actually seeing this. There's like a data center or multiple data centers behind that make this possible. But it's not only the hardware and the technology and the infrastructure, it's also a lot about software. So if we go a little bit back into the history when Google started, you see here like a usage graph from November 98 to April 99. And we did roughly 10x growth from 50,000 queries a day to like 500,000 queries a day. And if you see this graph, do you think that looks good? No, not really, right? It's like you don't want to see such a jigsaw graph. And for a matter of fact, during those days, if you went on to try and get like some search results during lunchtime, California time, you were probably out of luck. So we had a lot of like downtime or very, very long query times during that time. And what not a lot of people know, at that time, Google wasn't very rich. Google had no money. So we couldn't buy like ever bigger machines to accommodate that growth and basically build a reliable service by basically buying really reliable hardware. Just doesn't work at that scale. To emphasize on this, let's assume you have an IBM mainframe which fails only once every 10 years. Now you build software that has like, and you have a couple of other devices as well which are involved to serve like a search engine, right? So we have things like servers, routers, network, all kinds of things. And if you combine all of these, you end up easily in the thousands or hundreds of thousands of devices that are, or parts in your infrastructure that you need to be reliable to serve your applications. Now, if each of those would have like a mean fail time of once every 10 years, if you have 100,000 of these devices, one of those fails every hour, right? So it's just unachievable with hardware to build really reliable systems. So Google very early on embraced this to build their software in a way that they embrace failure, and that they basically, one of the first things is like how to deal with failure, right? To basically build really reliable and performant and scalable applications and services on back then very cheap hardware. So if we go a little bit further, and you see here that timeline starts in 2002. Like the first couple of years during Google, we were basically scrambling to keep alive, right? If we are down all the time, nobody uses Google, right? So we were like scrambling to get our search engine very reliable and index the world basically back then. And then in 2002, we started basically building the system in a more structured way and also publicizing papers around this. So the Google file system is one of the first things where we basically look at like how do we build a distributed file system which is very reliable and even in the case of failure. Another thing is since we basically were betting on many machines rather than very one large machine, our engineers had to deal with all the things that are coming from distributed systems. And early in the days, Jeff Dean and Sanjay Gamawat, they were looking at like, okay, our developers are pretty much everybody's doing the same things. Like, how can we simplify this? How can we build a framework around this to basically take away from them the burden of doing the same things again and enable them to actually innovate, writing new software, innovative software, rather than dealing with infrastructure. And one of the things in the data space there was the Mapreduce framework and model. Now the Mapreduce, probably most of you know it, just to very briefly iterate, is if you process a large amount of data, you basically, if you want to do that in a distributed way, you chunk up your data, you pick out a key out of each of your data pieces, so to say, you shuffle them around by this key, and then you run like aggregations over that, like you group or do aggregations by this key. Now this model is super powerful. You can pretty much get every data processing algorithms into this model, but you might have to modify it beyond recognition, right? So even though this enabled already Google to innovate and get more insights out of the data that we were collecting, it still wasn't the holy grail. It started off like a whole like open source environment, but still we were at the point where we had this, but the connecting pieces between multiple Mapreduce jobs, for instance, weren't there. So we had to further innovate, and we did within Google. Another thing is that more and more like people were looking for very recent and very new information. So if you type in Google some like Champions League game or Europe League game, for instance, you want to have the score showing up what's going on right now, right? So traditional batch systems, if you look at them, they usually chunk up the data by like hours or by day, and you have this latency to get this insight into your data. Now, if you want to get insight in your data, like more in like near time or real time, you need to actually process the data that is coming in that you collect like right away. So we developed quite a couple of frameworks and tools around that to get this, to bridge basically the world of batch processing, data processing, and stream processing. So if you look at like a more traditional approach to do this, and that was like many times, like in the industry still like the standard, is that it is assumed that a streaming system is just an approximate. So a streaming system, you basically get your data out, but you don't trust this data really, so you take it as an approximate, and you use your batch processing systems to actually get the like correct data. Now, scenarios for this is, for instance, you have like a pricing or billing pipeline, so you do this in batch. And then you want to have like price estimates, and you do this in a streaming so that your users know roughly what kind of consumption you have. Now the challenge with this is that you basically build up multiple teams that maintain these systems, you build multiple teams that have to learn different kind of frameworks and maybe even languages to accommodate these tasks. And this was also something that we wanted to address. We wanted to remove this barrier of thinking in these two kind of silos that you have to reaccommodate at the end. So we built a system that actually can do batch and stream processing in one API and in one framework. And that is Data Flow and Apache Beam. So how do we do this? And I just want to briefly look into this, which is, I think, is key to be able to get correct results even in a streaming fashion. The way that we did this, it sounds very simple actually when you look at it now, but to actually look into, to find that out and build a system around it wasn't that simple at the beginning. So now what we really have to do is, if you look at systems that collect real-time feeds, you basically have a system which can go out of things in terms of when your data is actually happening, when is actually something produced in terms of events, and when these events are processed. So a lot of systems that you see out there, they basically process your data, your streaming data, at the point that this is available in your system, and then they take these timestamps basically when they come in. What happens with this, and you see this in this red graph, is like your system can go out of sync. Basically, you build up a backlog, your system cannot accommodate all the data that you are getting into your system, and then you basically produce wrong results because you build up this backlog and your data is processed at in the wrong time frame of when it actually happened. So what we did in data flow is we specifically differentiate between those two times. We basically say, okay, we have the time when the event occurred, and we have the time when the event is processed. And what you end up with is actually a system where you can tweak your correctness based on these two times. And you can basically define and say, like, okay, at what point do I actually emit a result from when I do an aggregation over a certain kind of window. And you get to a near real-time system getting results that are actually correct, and you don't have to rerun in a batch processing. So we open sourced this API and an SDK around this, and call under Apache Beam. It's now at a top-level project at Apache, and it enables you to basically write pipelines, data processing pipelines where you can do batch or stream processing and run it on multiple runners. What is a runner? A runner is basically what executes your pipeline underneath. And that runner can be, for instance, Apache Kafka, Apache Flink, or it can be Spark or things like that. Of course, you can also run it on Google Cloud Platform in Dataflow as a fully managed service. So I have a very little demo here if you want to get out your phones and click on this. I'm going to show one second, show that here. All right, so I'm going to leave that up here so that you can do and I'm basically explaining really quick like how the pipeline behind this looks like. Let me get that out of the way here. All right. So what am I doing here actually? So in this little example, it is when you open it, you get four color spots, and you get assigned a color, and you're playing in a team. Now basically, it's a reaction game. You have to tap on the color where it is every time it changes, and we calculate behind the scenes a score for you, like what your hit score is and your team score. And I'm processing this in a data flow pipeline. Now, when I did this, I wasn't like an expert of like setting up machines or things like that. I didn't want to deal with this. I really wanted to have my problem, write a pipeline in a logical manner, and then just basically give it to an infrastructure to execute. And that is exactly what Cloud Data Flow allows you to do. So I just want to show very briefly a little bit of code here, because you're an developer audience, so I thought I would be safe to show a little bit of Java. So what is going to happen here? So basically what I'm doing in the beginning is just like reading some pipeline options. So you have to do a little bit of setup, like what project do I write to and things like that. The next thing that I'm doing is I'm using Cloud PubSub, which is our message bus, like fully scalable and global, which basically receives all the events when you're hitting on a color. And I take this from this PubSub queue, I basically start my pipeline and read in. Now, one of the things which is always good practice, I just write it back to BigQuery so that I can do some analytics later. If I have some new questions, I just write it back. And then what you see here in the middle is what I just talked about. I talked about this differentiation between when events happen and when they are processed. So what I'm doing here is I put all my events in a 5-minute window. So when an event happened, For 5 minutes, I put that in one window and calculate basically an aggregation over these 5 minutes. Now, I don't want to wait for 5 minutes till I get a score. You don't want to play this game and wait 5 minutes till you get like your hit score. So what I'm doing is basically I'm giving estimates for this window already. Like every 10 seconds, as you can see here, with triggers, I basically, every 10 seconds, I want to have a like pre-estimated result. And then even if elements come in late, so if I assume I have seen all the elements for this 5-minute window, I basically close this window. But I can still allow, if any like data comes in late, you were on a flight and you basically, I support an offline mode, and then you come out of your flight and you turn on your phone and suddenly all these events come into my system, I can still handle these events and can basically correct certain things after the fact. And last but not least, what I'm doing is basically, so here as I'm doing the aggregations, so I have some player stats and have some team stats, and then at the end, I'm writing this back to PubSub, and I'm writing this back to BigQuery so that you can see on your screen basically what is going on. So let's see which team is winning, and I knew that Team Blue would win because you're all dressed in blue, right? Awesome. All right. So this is like, if you look at data processing, there are a lot of other tools within Google that you can do. So this is one of the newer tools, basically, where you might have to change a little bit of the things that how you do them currently. But we also offer things that enable you to basically, when you come from a world of Apache Hadoop and Mapreduce and Spark and things like that, to lift and shift these elements into Google Cloud Platform. So we have a service called Dataproc, which allows you to spin up like thousands of cores within 90 seconds. And then you can run your Mapreduce job. And if you don't need it anymore, you just turn it down and you only pay for what you use. Now, another disruption within the company, like which enabled a lot, is our innovation in the compute space. So one of the things is which we embrace very heavily is containerization. So Google was very early on one that basically saw the problem of like people logging in and SSHing into a machine and setting it up is not going to scale. Right? So you need an infrastructure that you manage as in the most automated way as possible, and you basically want to have a system where the developer doesn't think anymore about machines. I mean, the developer thinks about his code, he thinks about what the endpoints are, and he thinks about the resources he might need, but he doesn't want to deal with like where this code is running and how it's kept alive and things like that. So within Google, we were early contributors to the container space, and like containers are around for many, many years, but they become really popular with the democratization in that space through, for instance, Docker, which built a large community around it and a great tool set to actually give containers to the everyday developers, and not only the cracks in the Linux space. So I just want to get a feel like who, because I don't think I will see the ones that don't raise their hands if I ask who has seen Docker. I want to know like who has not played with Docker yet. Okay, there are a couple. Who has not seen or played with Kubernetes yet? All right, cool. So my demo is all right, spot on. And that will help you actually on the competition that was just talked about earlier. So what is Borg? So Borg is our system which enables you in a declarative way to describe your services and jobs that you want to run. So what you see here is basically, you say, okay, what is my runtime? So roughly an area where you want to run your application. You have a binary, of course, we need to know what you are running. Then you give like, what are your connection point to the outside and the real world? And then you describe basically your requirements. That will help us to bin packing and also constrain you if you run out of these requirements. And of course, you say basically how many instances of that you will run, like depending on the traffic that you expect or the traffic that you get, you can basically define on how many instances you need to run of this binary. Now, since we are Google, let's start with 10,000 and not with 5. So how does that look like? What is actually happening if you send this declaration to Borg? Now, Borg is a system which basically manages a lot of resources. And you can think of like you have a machine which is called a Borglet. So you get like an OS and it registers with the Borg master. And each of these machines basically looks pretty much the same. Like you have some specific, but let's assume they look the same for simplicity. Now we have a Borg master system which is which has failovers and things like that, and has a store which is controlled by Paxos to be sure that we are strong consistent in the changes that we are doing. Now, the first thing that you do is you build your binary that I just mentioned, like you have a little app server, and you push that to a registry. The next thing is you write this declaration file that I just mentioned, which doesn't talk about like how to set up your application or things like that. It just says like, this is the application and I want to have 5 instances figured out, or 10,000. We commit that to the Borg master, and then you have a scheduler on the side, which basically checks what is the current state that is expected in my system, and what is the state which is actually happening, what is the actual state of my system. And it will calculate the differences, and based on the differences, it will instruct through the Borg master what should happen with this binary. So in our configuration here, we had like that we want to have 10,000 instances of our application. This was committed to Borg. Now the schedule checks and it's like, okay, there should be 10,000 instances, but I see 0. So the scheduler makes a plan of like where to put these 10,000 instances. And then the Borg master basically executes that plan. Each of the Borglets basically gets like, hey, you are responsible to run 3 of these instances. So they will basically pull down the image or the binary and then run this instance. Now what you can see what happening is like a ramp up of these 10,000 instances. And some might ask like, okay, why is this such a like somewhat shallow ramp up? Now, you can imagine we don't want to bring down our infrastructure. So this shallow ramp up is on purpose. The reason is if we would like basically tell 10,000 instances to pull the binary at the same time, like our network would also probably be like a little. So basically we do on purpose a shallow ramp up, and that is all controlled by the system. But what you see here is that the developer didn't have to deal with any infrastructure, in the sense of he didn't have to SSH into something or install software or things like that. Everything is basically packaged in this binary, which we, let's call it, have as a container here. Now, Borg enabled for us a lot, and you might have heard of App Engine, you might have not. I will not go into the details, but App Engine is one of the first services in the platform as a service, and you could like almost say function as a service, which is hip right now, space, but way too early. So at that point, when we publicized this or made this service available, based on the experience that we had in our internal systems with Borg, people weren't just ready for that. Like, this is just out of the world, basically. Like, what? I cannot SSH into my machine? Like, how am I doing that? So it took a while, basically, for the industry to pick up and to embrace that kind of way of developing and basically going towards a more cloud-native application development and innovation. Now, what we did and what took off, which was publicized and made available at the right point in time, in my impression, is we took all the learnings that we did out of building Borg, which, as you can assume, since we started in 2006 there's a lot of legacy in the system. We made a lot of learnings which we could have not really fixed in our internal system, but we basically said, okay, there should be a system out there that does the same thing as Borg, but actually even better. And that's where we wrote from scratch Kubernetes and open sourced it and gave it as a seeding project to the Cloud Native Foundation. So what is Kubernetes? Well, Kubernetes is pretty much a Borg. It's a way where you use declarative configuration files to instruct the system what you want to have as a state, but not how to get to the state. So think of like there are a lot of systems out there where you have a beginning state and you give all the instruction how to get your point B from point A, but then they stop right? And if point B is like degrading over time, nobody really takes care. Like you have to think, like you have to watch, or you have to like monitoring systems and whatnot, and it's complex and difficult, and you have to manage all this. Now Kubernetes has basically all these things built in. They are built in the way that you only define B. You only say this is my B state, and you don't describe the way how to get from A to B. And what this enables is a lot of innovation under the hood. It enables a lot of innovation of like how to run your applications without you having to rewrite any of your applications. So I want to do a simple, brief demo around this. So what you see here is, and I'm starting more and more writing Go code. Really amazing language, a lot of fun to write. But basically what I have here is a very simple web application. So what I do is I have 2 endpoints here. I want to like relay my host name, and I want to say hello bol.com when I like hit the hello endpoint. And then I open a server which listens on my port 8000. Now, what I'm doing is, I want to like build a binary which has all the dependencies based on a very standardized standard Linux basically, and that runs this. Now what I'm using is Docker basically. I want to package this into a container, and what I'm doing here is a little trick, because if you build like the tools that you need to build your Go binary, they are quite big. Right? There's a lot of there's an ecosystem around this, and you need all the kinds of compilers and things like that. And your build container ends up to be a couple, I think a couple of 100 megabytes actually. We can actually check and see here. So we have this build container here, and I can just ask Docker. Let's see. Can you see this? Should I make that a bit bigger? All right. This doesn't help you, but me. So let's get all the images and grab for this. Let's see if that works. No, of course, doesn't work. Demo fail? It has to be. All right. So if you look at this, we see like my Golang build container is 257 megabytes. And I already use now the Alpine version, which is a lot smaller than if you use the Ubuntu-based or the Debian-based version. But you can imagine if I have a container this big and I want to like instantiate like 50 or 10,000 instances of it, I'm really like putting a lot of bytes through my network and occupy a lot of bytes on my hosts actually. So what you don't want to do is you don't want to like have your build environment also packaged in your container. So I do a trick here. I have a build container which builds me a statically linked binary, and you can see here basically how I'm doing this. You can ask me for details afterwards. And then I basically just copy that binary into my run container. And this, if we have a look here, I have my demo app here. You see here version 0.1 is 9.81 megabytes. So that looks a lot better for me to run actually an application. So the first thing that I'm gonna do is I have a Kubernetes cluster. So I like to create my Kubernetes cluster in Google Cloud Platform, as you can imagine, because it is easy, and you basically run one command and you get like a cluster. And this is my cluster. It has still the notions of node, but you as an application developer don't have to really care. This is like still a little bit of the administrator job here. But what I want to run is I run my container. So what I'm doing is I have a fancy makefile. And that makefile, with every project in Google Cloud Platform, you get your private registry, which is only visible to you if you wish so by default. And if you wish to make it public, you can make it public. But as you can see here, basically I'm building my container, my binary, and then I package that into my run container. And since I have done that before, you see that was really quick and pushing that to my registry. So now what I can do is I can run my application. And if you can see here, let me actually get that bigger on the screen. You can see here I run my application. I give it a name, in this case, demo app. I point to the image. So this is my private repository, demo app 0.1, and I say on which port this runs. Now, when I do this, there are a couple of constructs created within Kubernetes. And they are all held together with something. So let me talk a little bit through the constructs. So the basic, very basic construct that you have is a so-called pod. And the pod is basically your container running. The pod can contain multiple containers, and it basically, like, you can define like environment variables and all the things. I don't want to go into detail here. But basically, your pod is like your immutable atomic unit that travels through a Kubernetes cluster. Now, your pod, like as lives, it gets an IP, but you never should use this IP because this IP is ephemeral in the way that, like, this pod could be stopped and rescheduled on a different node, and you shouldn't rely on the IP. But let's say like this pod is where your container runs in. Now this pod needs to be controlled somehow. So this kubectl run command that I just did is actually creating a couple of constructs behind the scenes, and these constructs help me to keep that state alive that I want. I want to have this container running. So what is created is a so-called deployment. And deployment is a construct which manages my my pods through a different construct, but let's say we have a deployment, and I can say in this deployment how many instances I actually want to run of this pod. So in the case here, as you can see, I have currently only one pod running, and I can scale up and down, and I'm going to do this in a minute. Now, I cannot talk to this pod currently, because I mentioned it has an ephemeral IP, and I haven't linked it to the outside world yet. So to link it to the outside world, I have a construct called a service, and I just use this. So basically, kubectl expose links my demo app that I have, which is a deployment that you see there, and I'm saying type load balancer. What's now type load balancer? So by default, services within a Kubernetes cluster are cluster private. So you can only talk to them within the cluster. Now when you want to make them publicly available to the outside world, you want to use a load balancer. On GCP, that creates automatically and provisions for you on one of our global load balancer, basically an endpoint for you. So I'm going to do this, and I'm going to watch that actually being created. So it takes a little bit of time to actually get that external IP address. So while this is doing, I'm going to show you really quick how this deployment looks like. So somehow you have to keep all these things together, right? And what's behind this is a configuration file. And to keep all these things together, like that the service knows what pod to talk to, and that the deployment knows which pods to take care of, we have a construct called labels within Kubernetes, which are orthogonal and give you the possibility to basically manage these different constructs and query on them. So as you can see here, we have like this label demo app, and then you see down here on my container, you have also this label demo app, and that's what basically keeps all together. What you also see here is things like how many replicas do I have running and things like that. So there's a whole like very powerful configuration language behind this to do a lot of things with these. All right, so we got our external IP address, and what I want to do now is I actually want to run and see my host name. So now you can see basically I have one pod running, and that is exactly the name that you got when I did kubectl get pods. You see the same host name, right? So now what I want to do is I want to actually scale this. And let's scale this to 3 replicas. And I do kubectl get pods, and you can see like this is so quickly that they are up. It's just, right? You can just scale out and in like very easily. Another really cool thing about this, and I want to show that really quickly, is I'm gonna do my application update. I want to have my version 2 of my application. So, so let's do and change also my version, of course. I want to have version 2 now, 0.2, and then I do a make push GCR, which basically does everything of like building my container, building my static like library, putting that static library into my run container, and then the last point, what it is doing is pushing this to my private registry. So while it is doing it, I can do something really cool and can basically say, oh, right now it's not deployed, just to show you that this is really like the old application running right now. I do shortly this. So you see here, this is only going dark bold.com. So my old application is still running. Now, what I can do is I can actually go into my deployment. And you saw down there that the my new version was pushed. So I can just go here and search for, let's go here. And do 0.2. And I basically just live deployed my new version. And if we do this, you see here it's already new version is running, right? So this is really, really powerful what you can do with Kubernetes. So now that's probably, I mean, this is like going on for many, many years, and there are a lot of like innovations in the compute and data processing space. But the more recent, and probably what you all waited for, more recent developments and innovations are in the more like artificial machine learning space. So one of the things that I want to touch on is Tensile Flow. So Tensile Flow is basically a framework and APIs and the tool set which we developed within Google to do machine learning, to basically have algorithms learn, not tell them what to do, tell them how to learn. And I want to take one use case here, what this is actually enabling in our world right now. This is a picture of a cucumber farmer family in Japan. And the guy that you see in the back that looks a little younger than the other two folks in the front is the son of this pair. So his parents are cucumber farmers. And what they do every day basically is they have different kind of qualities of cucumbers, and you get different prices of that. So his mom basically sits there all day long and sorting cucumbers. And he thought, like, it's a really tedious task. This should be something that is possible to do with machines. So he's not a computer scientist, but he's an engineer. And he heard about TensorFlow and sat down and was like, okay, I need to figure this out. So he built actually a system with TensorFlow and trained a model to differentiate these different kinds of qualities of cucumbers. And he built a little prototype based on a Raspberry Pi, where he basically first, like with his mom, categorized all these cucumbers. So he showed the TensorFlow model, basically, here, this is category 1, this is category 2, and let like the neural network learn how to characterize these different kinds of cucumbers. And then he deployed this model like to get his predictions on these cucumbers onto a Raspberry Pi and built this little robot thing to do actually the sorting. Now the amazing thing here is really that this was not a computer scientist. This was not somebody who has a PhD in machine learning or artificial intelligence. This was like an everyday person like you and me who can do that. And that, I think, is pretty impressive. Now, what can you do on Google Cloud? And there's a little bit of like a pitch here, but basically, you have two kinds of worlds that you can start in. If you are very affine to mathematics and you basically get a kick out of neural networks and like, I'm losing the term, but basically like in math, then you can start on the ground and go towards like the TensorFlow route and build your own models and train them and run them on Google Cloud Platform. So we have a Service Cloud machine learning engine, which basically gives you, like, takes away the care of like any infrastructure. You can deploy your machine learning TensorFlow models there that you want to train, and we provide you the sources of CPU and GPU there. But like for the everyday person like me, I'm more going to the other way and use some of the pre-trained models that we have on Google Cloud Platform. So we have a couple there. We have like the Vision API that allows you to basically recognize and label pictures. We have Speech API, which can recognize languages in over 80 languages. I haven't the demo for that, but I'll show you something else. We have a natural language API, which basically can take your text and can get sentiments out of your text. I'm going to show you a little bit of something about this. And we have, what's just new is our Cloud Video Intelligence API, which allows you to basically label parts in your videos. So I want to start with the Video Intelligence API. So what you can basically do is you can run your videos through the API, and then you can label like what is happening in your videos. So for instance, since we have a lot of rain out there today, I want to see some beach. So if I basically search for beach here, I see like we have a video about Barcelona. I can go into this and see here that like the video API actually saw a beach. So that is really, really great. Like, so you can process a large amounts of video and basically pick out the elements which are relevant for you. Very powerful. Another demo that I want to show is, feel free to, there's actually a life hack right before the talk. I had to change the number to the correct number. So I did an inspect in Chrome and changed the number, so I shouldn't reload this page. So what is this demo doing? So this demo is actually using Twilio in this case. So you send an SMS, you can send your sentiments about like this talk, if you like it or not. And it is sent through Twilio to Cloud Functions, which is our like serverless offering. Now I won't go into details what means serverless. There are servers running behind Cloud Functions, just to kill that myth. And Cloud Functions basically calls our NL API, gets sentiment out of the SMS that you send us, and then the response to BigQuery, and also gives you some response as an SMS. And you will see what kind of response that will be. So there's a lot of, like a multitude of possibilities that you have, like with machine learning, with like data processing and compute on Google Cloud Platform. Now there is one thing that I want to mention here. What is the future outlook in like, especially in the machine learning space? And I want to mention one thing is, I talked a lot about software today and not a lot about hardware, but there are some certain things where definitely the hardware innovation brings you quite a big step forward as well. Now we have within Google a lot of hardware innovations, especially in the network space and our data centers, how we operate our data centers, and things like that, how we use machine learning in data centers to have them really effective. And what we also built is a hardware unit which we call a tensor processing unit. Now some might ask, like, okay, I have a lot of processors in a graphic card. Why do I need like an ASIC for TensorFlow? The thing is, there are a couple of things. Like graphic cards are doing a multitude of things. So they are powerful, but if you run like machine learning on them, like most of their resources is not used. So they're basically like kind of like an energy overkill. If you build a like very specific processor to do your machine learning, in this case is as the tensor processing, you can basically be very effective. And this is, as you can see here, 180 teraflops per chip. And we can build like really powerful nodes of processing tensor. So what is doing this is we can take away a lot of like the caches and things like the accuracy and precision of what you have in GPUs, because this matrix, these are specialized for matrix multiplication, and we don't need these high precisions for that. We figured out that like even a lower precision gets us really good learning with these units. Now, we make these available currently as a private alpha, but we're going towards making them available for everyone, that you can basically run your TensorFlow models on top of TPUs. So to recap, we have seen a lot of like innovations in software and hardware which was going on in Google, and we claim to be, or we want to be, like the open cloud. So one of the things that you see here is that a lot of the technologies that we built inside of Google, we publicize through papers, and recently also publicizing and making more of our code open source. And you see, I don't want to go through all of these, but you see a lot of these services that we are running to run our business internally, we make directly available to you to build your applications on top of this. So we are not like new building these services. We, like many of these services, some we build new, of course, but many of the services that we are providing for you are battle tested in a company that has over 7 applications which have over 1 billion users, right? So you can be sure that these do scale, and we have a whole team around and culture within Google that makes sure that these are running and very reliable. So I stepped through, and Google did this transitions as well, and I just want to like close with that frame here. If you look at like how cloud came along and like what are the different stages of cloud are, we basically start in having like the first wave of being like co-location, and Google started out with that as well. When we had like our 5 servers and we're running a website, we basically were in a colo facility and putting our servers there, and we had to manage everything ourselves. So we got we got network, we got power, and we got maybe cooling. And since we put too many servers into some of our locations, that some of them burned up. But anyway, because cooling wasn't like sufficient enough for handling the heat that we were producing, but things like you basically start out and you get like the connections to the internet and power, but everything else you have to manage. Now the next phase was like virtualizing. So you basically were like many times these machines were underutilized because you wanted to have a buffer of growing. Now virtualizing allowed us with VMs and then containers nowadays to actually put multiple applications on one server without having them like to affect each other too much and be like contained by themselves, and you have enabling better resource utilization. But you still manage things like your OS upgrades and things like that. Now, if you go to the third wave of cloud, you're going actually into a world where you don't deal with these things at all anymore. So you're really going into the way of like becoming more like a cloud native app developer, where you think about your application and how you innovate, and you give it to somebody else to run it. And that is the third wave of application. You have a lot of our products that are coming out and that we have already that are like embracing this cloud native fully managed services, where you don't think about machines anymore as such. Maybe sometimes you have to say like, okay, I want to have 3 nodes or 5 nodes, but everything else is taken care of for you, and you really can concentrate on getting insights out of your data and innovate and getting your company forward and keep this a really great place to work. So while we went through all these phases, we built an infrastructure that we make available for all of you. And with this, I want to thank you, everybody, and open up for some questions. I think we have like 3 minutes, maybe. Yeah. Any questions? Otherwise, like last point, I'm gonna be around with Matt and Lawrence for the majority of the day. So if you have any specific questions, as mentioned, like I'm the advocate, I like to get your input, how you use your products and what like complications you have, or where you want to give constructive feedback. I know that some of you are already working with Container Engine or Kubernetes or things like that. So please find me. I will be around and happy to chat with any of you.
Anyone? Yeah.
So,
Robert,
yeah.
could you repeat the question?
Okay, if I got the question right, so basically, if you build this culture or like the infrastructure in a way that your developers that innovate only know like the abstraction above and they don't know the specifics underneath anymore, what happens in the case that something goes wrong and you need actually the people that know underneath? So, of course, like you have still people that are building these systems. And in our case, basically, you have Google that are building these systems and that understand the system underneath. So you will have people that understand that. But it will be like what you take away is basically that everybody has to know this, right? You have your experts in this space that can help you, that basically sometimes you might have to adjust the product underneath, or sometimes you actually can teach the people that building on top how to do things different to not run into the issues that you're running into. So it's a bit of like a cultural change in the way that like people, like you take away some of the like, or you concentrate some of the knowledge to like a smaller group of people so that you can free up the majority to help them innovate and thrive much faster. I hope that addresses somewhat. All right, thank you. Oh, yeah. Yeah. So in many of our services, so like I mentioned that for some of our services, you still have to say like how many nodes. But many of our services allow also for auto-scaling. In some of the scenarios, you don't want that. So there are scenarios where you basically, like you need to them like kind of like some check and balances. So, so there are two words. Let's dive into one. And should I repeat the question? Sorry. The question was like, I was mentioning that you still have to sometimes say nodes and you want to actually dynamically scale. Why do you still have to basically define how many nodes you or instances you have for certain service? Now we have two worlds. So there's like the world of, for instance, if you look at data store, you have actually a fully scalable systems where you don't define anything in terms of nodes. This system scales from the start of your application to becoming like $1 billion application, like Snapchat, for instance, right? Which was built on top of App Engine and data store. And it was just scaling basically seamlessly. Now we have others where, for instance, like Bigtable or Spanner, for instance, which is our horizontally scalable relational database, where you still define how many instances you have. And yes, you can build an auto-scaling around it, but you also want to have like some check and balances. So if you don't want to, if something goes rogue, that this basically scales like crazy and incurs like an insane amount of money that you incur, like you have to pay. The other thing is also you want to be, like sometimes we haven't quite figured out the right way to basically give you the control and way of like, what is actually the scalability that you want? In a way, sometimes you might want to do like, okay, I accept a little bit longer query times by paying a little bit less money. Now, how do you quantify this basically in an auto-scaling scenario? So we are working on like making improvements there that we remove more and more this notion of instances. But right now we have still a couple of products where we want to give you the control of like basically saying like what's your scalability limits that you want to have. And you can build a system around, some of them have it out of the box that we have, where you can do the auto-scaling, where you can say, okay, I start with 3 nodes and please go up to 10 nodes in case of these kinds of metrics happening. Right. Thank you very much.